What if I told you that you could solve a tricky puzzle not with a bunch of complicated algebra, but just by drawing a picture? Well, today, that's exactly what we're going to do. We're diving into the surprisingly powerful graphical method for solving pairs of linear equations. Let's get right into it.
So here's our game plan. We're going to start with a fun little puzzle that takes place at a fair. Then we'll see how we can translate that story into the language of math. From there, it's all about drawing a picture to reveal the answer. Along the way, we'll discover that there are only 3 possible outcomes, learn a really clever shortcut to predict them, and figure out why sometimes a picture is the most powerful tool you've got.
You know, every great math problem really starts with a good story, and ours begins at a village fair. The first step is to take this fun day out and turn it into a question that math can actually solve. So let's meet Akila. She's having a great time at the fair, but she's given us a puzzle to solve. Can we figure out exactly how many rides she went on and exactly how many games of hoopla she played?
Okay, so to solve this, we need some clues, right? And luckily, we've got them. First off, we know her budget. She had 20 rupees and she spent every last bit. We also know the prices. 3 rupees for a ride on the giant wheel, 4 rupees for a game of hoopla. And then, here's the kicker, the most important clue. The number of games she played was exactly half the number of rides she took. All right, now for the really cool part. We're going to take Akila's story and translate it into a completely different language, the language of algebra. This is where the real problem solving starts. And this slide just lays it out perfectly. On the left, you've got the story. On the right, you've got the math. We're going to say the number of rides is X and the number of games is Y. So that clue about the games being half the rides, boom, that becomes our first equation. Y equals 1/2 X. And the clue about the cost, 3 rupees per ride plus 4 rupees per game adds up to 20. That becomes our second equation, 3x plus 4y equals 20. And just like that, our story puzzle is now a math puzzle. So we have our 2 equations. What's next? Well, we're gonna draw them. See, each of these equations can be drawn as a straight line on a graph. And that line, it's basically a picture of every single possible combination that makes that one rule true. But here's the thing, right? The answer we're looking for has to make both of our rules true at the same time. And on a graph, there's only one place that can happen, the exact spot where the 2 lines cross over each other. That single intersection point, that's our solution. And this leads to a really fascinating idea. When you take any 2 straight lines and draw them on a flat surface, there are only 3 things that can possibly happen. Understanding these 3 scenarios is the absolute key to solving any problem like this. First up, the most common outcome. The lines cross. They intersect at one and only one point. For our puzzle, this means there's a single, unique answer. One specific number of rides and one specific number of games that works for Akila. And you know, there's a name for this. Anytime a pair of equations has a solution, it doesn't matter if it's one or more, we call it a consistent pair. It just means the clues aren't contradictory. A solution is actually possible. Okay, second possibility, what if the lines are parallel? You know, like railroad tracks. They run alongside each other forever, but they never, ever cross. If our 2 equations give us parallel lines, it means there is no point they share. In other words, there's no solution. And yeah, you guessed it, there's a name for this one too. It's called an inconsistent pair. This means the 2 clues we were given actually contradict each other. It's like asking someone to find a number that's both even and odd at the same time. It's impossible. There is no solution.
All right, so on to our third and final outcome. This one's a bit of a special case. What if our 2 equations are actually describing the exact same line? They're called coincident lines. It's like they're lying right on top of each other, sharing every single point. This means there isn't just one solution, there are infinitely many. So what do we call this? Well, it's a dependent pair of equations. It basically means our 2 clues were really just the same clue, maybe said in a slightly different way. And since it technically does have solutions, in fact, tons of them, it's also considered a consistent pair. So you might hear it called a dependent and consistent pair. Now, drawing graphs is super helpful, but what if I told you there's a shortcut, a cheat code almost, a way to know if lines are going to cross or be parallel or be the exact same line just by looking at the numbers in the equations without drawing a single thing? Think of this table as your crystal ball.
Seriously. And don't let the word coefficients scare you. That's just a fancy term for the number sitting next to the x and the y and the constant number at the end. As you can see, all you have to do is compare the ratios of these numbers between your two equations, and you can instantly predict the outcome. It's an incredibly powerful shortcut. So, if we have this awesome shortcut, why even bother with the graphs in the first place, right? It's a fair question. Let's talk about the real power of drawing the picture. Okay, let's break it down. The absolute beauty of the graphical method is how clear it is. It gives you a visual of all the possible answers, and it just makes sense intuitively that the one spot where they cross is the one true solution. But, and this is a big but, it's got one major weakness. If the answer isn't a nice, clean, whole number, if the lines cross at some messy point, like, say, 1.75 and 3.3, it can be really, really hard to read that exact answer off the graph. For those cases, we sometimes need other methods.
And that leaves us with something to think about. We've seen how powerful equations can be, but we've also seen the incredible clarity and intuition that a picture can give us. So I'll leave you with this question to chew on. When it comes to solving problems, not just in math, but in anything, when is a picture truly worth more than an equation?